Here what we're going to do is we're going to define what a power function is. Then we're going to look at the behavior, specifically the end behavior of power functions. And so what a power function is it's a function that takes the form of a times x to the n. So think, just to throw out some examples, you could have 2x to the fifth, you could have negative 8x to the third, you could have 1/2 x to the 10th. These are all power functions. So it's almost like, maybe think of them as like the leading term to a polynomial function. And the thing is, what we can do is if we can look, we're going to notice there's certain patterns about how these graphs look based on this leading coefficient that we're going to call a, and based on this exponent that we're going to call n. And so what we're going to do is we're just going to look at patterns there and see if we can make predictions based on those patterns. And so here's what I've got. So all of these graphs are going to fall in one of four categories. We're going to have like a positive a value or a negative a value. And then we're going to have that n exponent. It's either going to be an even number or it's going to be an odd number. Okay, we're limiting it to positive whole numbers for now. Or I guess I should just say whole numbers. Now what I'm going to do is I'm going to pull, and we're going to see how this works. I'm going to pull a graph. I'm going to pull Desmos over here onto the right side of our screen. Uh-oh, not going quite how I'd hoped. Okay, now I'm ready. So what I want to do is let's start by looking at what would be this like top left corner. So let's pick an a value that's greater than 0 and an even exponent. So an a value that's greater than 0 would be like 2, and then an even exponent would be 2x squared. Well, that's just a quadratic. So we see it still like that, but what happens is I change that to the 4th power, or to the 6th power, or to the 8th power. Any other even number, you can see that it's going to have that end behavior that's almost like a U. It's going to be what we call matching end behavior. It's the same on the left as it is on the right. And let's see what happens. Does anything happen as I change this to other positive numbers? Doesn't look like it. It looks like it's just going to control the vertical stretch. So what we know here is we know something about this graph. I want you to, maybe in your notes, just draw a function that looks like a smile. It's going to have matching end behavior. It might be stretched, okay? It might be a little bit more boxy, but for the most part, it's going to go up and to the left, and it's going to go up and to the right. That's always going to be true in this category, okay? Now, let's move on to this category. I'm sorry I'm leaving it blank, but I can't write and do Desmos at the same time with this program. But let's go to where n is odd, and let's see what happens. So if I change my n value up here to an odd number, but we're leaving our a value as a positive, so I'm going to leave it as a 4, but let's change our n to other odd numbers, and let's see if it kind of always takes this form. So if I go to 5, and then to 7, and then to 9, and then to 11, and then to 111, we can see that our, even to 1, even an odd number it shows true. But what we see is we're going to have what we call opposite in behavior. As my function, as x decreases, our function is going to go down, and as x increases, our function is going to go up. So it's kind of like a cubic function. We know that the basic cubic function is going to look like this, and any time I have a positive leading coefficient and an odd exponent, our function is going to take this general form. It's going to have this general end behavior of up and to the right, down as we go to the left. Now, let's move down here to this bottom left, and we've kind of taken care of these first two. Let's do the same game, but what about with a leading coefficient that's negative? So as I change this 4 to a negative value, and we have an even exponent, it looks like the only difference between this box here and this box here is that if that a value is negative, our function has been reflected. Meaning, like earlier we did 4x squared, now we're doing negative 4x squared. And so that pattern is going to hold true for any even exponent, for any even exponent as I go to 8 and to 10 and to 12. We see that we're still going to have that matching end behavior. It's going to go down and to the left, down and to the right. That's always going to hold true when we have an even exponent and a leading coefficient that's negative. It's going to have that same end behavior. Now, let's go to the last category. I'm going to leave my leading coefficient. The a value is a negative, so I'm going to leave that as a -4. I might play with other negative values there, but it is going to be negative. And then let's look at when our exponent is odd. So if I go to, let's go to 3, and then 5, and then 7, and then 9. So it looks like I'm always going to have that end behavior. What about with other negative values? What about negative 2? What does that do? Okay, kind of controls the stretch a little bit, it looks like. Negative 7, negative 9. Okay, and so to kind of go back to a more generic form, if I have a negative leading coefficient and the exponent is odd, we're going to have opposite end behavior. But here it's going to go up and to the left and down and to the right, which was the opposite of this one right here. So now what I'm going to do is I'm going to get rid of my graph, and we're just going to kind of summarize in a little chart, which I think is helpful. So if I have these power functions, and I'm looking at when a is greater than 0, I know it's a rough sketch, but we're going to have that matching end behavior. It's going to increase to the left and increase to the right. The only difference is when that leading coefficient's negative is that it causes that vertical reflection. So we still have matching end behavior, meaning if it goes down on the left, it goes down on the right. But it's just going to be reflected from this one up here. And then for our odd, when this exponent appears odd, we don't have the matching end behavior. We have what's called opposite end behavior. Meaning if I go down to the left, I'm going to go up and to the right. And then if I just made that leading coefficient negative, it would just cause a reflection of that, which would be here. So all of our power functions, remember these are called power functions, are going to fall in one of these 4 categories. And at least for the purposes of what I'm covering right now, you don't have to know the super specifics about what it looks like, but just know what that end behavior is going to be, because this is going to give us some insight later when we graph full polynomial functions. And so the last thing I want to do is I'd like for you to pause the video and see if you can just draw a rough sketch of what each of these 4 graphs look like. Try to do it without looking at your notes from the previous slide, but if you have to, you can. So I'm going to walk through these. This first one, we have x to the 4th. It's an even exponent, so that means our end behavior is the same. So I either have this or I have this, but since we have the negative leading coefficient, we know that it's going to be decreasing on both sides. So that is what our first one looks like. I'll move down here. Now we have an odd exponent, which means that my function either looks like this or it looks like this, because that odd exponent means we have opposite end behavior. Since the leading coefficient's positive, we have a function that's going to be increasing as we go from left to right. So I'm going to get rid of that one. Up here, we have an even exponent. That means my function will either look like this or like this. And now look, the leading coefficient, it's not really shown here, but anytime it's not shown, our leading coefficient is a 1, and that's a positive number. So that means since it's positive, we're going to have a function that increases on both sides. And then lastly, as I go to negative 2x to the 7th, as we look at that, we have the odd exponent, so that means we have our opposite end behavior. It's either going to look like that, or it's going to look like that. And since our leading coefficient is a negative, we have a function that's going to be decreasing as we move from left to right. So I'm going to erase that one. So the main idea of the story, at least for my purposes, is I want you to be able to look at this number that's a coefficient and this number that's the exponent and see which of these 4 categories your function is going to fall in.